and thank you all for coming out so early. We'll give you a gentle introduction. We're going to show the most recent trailer from Finding Dory.
Today's the day. Our field trip to the Stingray Migration.
Stingray Migration.
Migration is about going home, which is where you're from.
How do the stingrays all know where to go?
Instinct, something deep inside you that feels so familiar that you have to listen to it.
My mom, my dad, I have a family.
We will never forget you, Dory.
What if I forget you?
I miss them. You know what that feels like?
Yes.
Then we better get going.
Totally sick!
Isn't it great?
No! I'm gonna be totally sick!
Can you help me?
Sorry, not a great swimmer.
I think you swim beautifully.
Thank you.
You're welcome.
Wait, Dory?
Yes?
Dory?
Yes.
You and I were friends.
No.
It was so much fun because I'd tell you a story and then you'd completely forget about it, and then I'd get to tell it to you over and over again.
I'm looking for my family.
Are you crazy? It's too dangerous. Hands!
Hands? Mommy?
Holy Neptune.
That is definitely not Mommy! I'm sorry. I gotta blink. How do you hold your eyes open that long? Huh? What's happening? Hello? Hello?
Hey, you.
Hi. Can you help me? Not good.
All right. So today we're going to talk about real-time graphics in service of feature film production. And before we get started, I just wanted to kind of acknowledge the other engineers on the GPU team because they've done some really, really awesome work. And we're presenting it, but really it couldn't be done without them. So David Yu and Takehito have put their heart and soul into pretty much everything that you're going to see today. They're super awesome. Matthew Williams is relatively new to the team. He came from Intel and then Blizzard, but he's already done some really big contributions in terms of like adding multi-threaded, doing some multi-threading work inside of Hydra. So we have a really, really great team. It's awesome to work with them. All right, so overview for today, we're going to talk about challenges. We're going to talk about the tech that we've developed to solve those things. We're going to talk about some specific effects that are particularly useful, and then we're going to talk about future work. So in terms of challenges, we're dealing with production assets, and we try to consume those things in their kind of raw form, the same form that would be fed into RenderMan, but present them in kind of a real-time presentation. These assets have been optimized for beauty, not for real-time rendering, and so they tend to be heavy and really, really gorgeous, but a lot of data to deal with. This is our new hardware configuration. We upgraded from a Quadro 4000 to an M6000. So if only we could get a good GPU. No, I'm kidding. This is an awesome GPU, and the challenge tends to be just feeding it with enough, fast enough. And so we also have a 16-core Intel Haswell CPU and 64 gigs of memory. And these things are rack-mounted in our server farm, and so 2 users sit on a single machine, and they actually have 2 times this configuration. So if we can use 2 times the GPUs and 2 times the CPUs and 2 times the RAM, we can upgrade to that configuration for really heavy stuff too. That kind of becomes a challenge in itself. All right, so this is a shot from the trailer that we just saw, just to kind of motivate the scale of things. So this is like 6,000 meshes. It's like 81,000 instances. Just in this shot, this is like in frustum. This is after culling and everything. So 52 million faces on the subdivs. But then those faces get subdivided, so you end up with like 100 billion plus triangles. 100 billion is probably an underestimate. That was just kind of a quick number that was thrown out there, but it's probably actually a little more than that. And I think anyone who works on visual effects knows that this is actually a small shot. So for heavy assets, you have millions of instances. You have characters with hundreds of meshes. Interestingly, modern kind of next-gen or current-gen game assets for their human characters, they tend to be heavier than our human characters because we use subdivs and we have lighter meshes. But for things like cars, Mater, for instance, has 800 meshes in his character, and they're all kind of deforming. For crowds, they have tens of thousands of characters for large crowds. For large sets, we have billions of polygons in frustum, coarse face polygons that need to be subdivided. And then subdivision, of course, causes geometric growth and complexity. And I wanted to call that out specifically because for Pixar, that's the way that we model our assets, is using subdivision surfaces. And so for games, subdivision is kind of an interesting thing right now, and you can kind of take it or leave it. But for us, like we have to find some way to show the true kind of subdivision representation. The other two kind of challenges that I didn't call out here are that we've moved to path tracing everything with global illumination. So that's a challenge for production, and it means the render times have gone way up. And so that means that doing things in real time becomes more and more attractive. And so Finding Dory, I heard some numbers that the longest render times for the biggest shots were something like 600 hours per frame. So it's really, really motivating to find something that you can do fast in real time to give you a preview of what's going to come out of that final frame. Okay, so on to the actual solutions that we've developed for these things, for these problems. And so Presto is our animation system. It's used for previs, layout, simulation, rigging, animation, crowd animation. They also do some crowd simulation in Houdini, but the actual animation tool is Presto. And we want these departments to be able to work concurrently together on, like, for a single shot, we want everyone to be able to kind of work at the same time. And so one of the superpowers of Presto is actually solving that problem. And Dirk is going to give us a quick demo.
Hi, everybody. Thanks for coming. So to show you how we use these real-time techniques, we're going to do some live demonstrations of Pixar software on this laptop. This laptop features a NVIDIA 980M GPU with 1,500 cores in it, which is pretty awesome. So here we have Presto. A number of departments use Presto. We're going to focus on animation and rigging, just to give you kind of a quick intro of what happens. So here we have a shot loaded from Finding Dory. We have characters in the scene. We have sets in the scene. Let me switch over to main cam here. So this is the interactive environment that we... So this is the interactive environment that animators use. And you can see it's important to be able to give them an immersive view of this world. So here we have the viewer. This is our view into the three-dimensional scene. And we can go into different cameras, we can orbit around, we can look at different characters in the scene and see what's happening. Here on the side we can browse the objects in the scene. These we call prims. So here we have some layout light rigs, we have some sets in here. You can see those sets come on and off. The characters are down here. You can see those characters come. We have some cameras on the bottom. So these are the objects in the scene that animators will work on. At Pixar, we have dozens and dozens of animators, dozens of riggers, all working simultaneously on the film, and all working on different aspects of it. So Presto is a very collaborative environment. So an animator, for instance, will go into this character. Inside of the character, there's some geometry, and this is here we have some interfaces that character riggers have set up for animators. And if I open up this mouth, for instance, I'll see some attributes here. Those attributes which change over time are the things which control animation. So here, if I go in and grab say, like the jaw UD attribute, which is over here, I'll pull it over into MDT, named MDT in 1982 by Tom Duff, who wrote the original version. And so here, the animator can use a spreadsheet view to be able to move their character up and down. And clearly, we want to be able to see like how the wrinkles on Dory's nose are moving as her mouth moves up and down, and things like that. You can also go into the scene and grab kind of handles to move things around in real time. And if you want to, you can go when you really need to finesse the shape of these things, you can go drop these things into a spline editor and look at the shape of that curve and kind of finesse the movement over time. So this is kind of a progression that animators will do to be able to go and animate that movement over time to exacting detail. Like every pixel is analyzed a lot. So that's the interface that we need to create for animators. Let me show you another example. So this is Butch from The Good Dinosaur. I love this guy. The rigging is by Alonso Martinez, who's amazing. And so some of the things we also need to see is we need to see some of kind of the distortion and stretching of skin because the rigging system in Presto is built for ultimate control over shape. It's not built to be totally real time, although we do get some good speed with it. So here, an animator can take that character and move it around. And you need to be able to see, Alonso needs to be able to see on the back of that leg. As he moves the leg up, he's got some controls that then fire some muscles on the back of the leg to do some stretching. So, if you just have a wireframe, you kind of can't quite see how that affects. about now?
Oh, much better.
Better? Okay. Some quality animation there on Butch. As you go into his face, too, you want to be able to see he's got that big bite mark on the side of his head. So as you move his jaw up and down, it's important to be able to see how that scar stretches as the mouth moves up and down. And we have his actual surface mesh is this, and then we use displacement, real-time displacement in GLSL to be able to get a more detailed view of that. And then riggers will be in this environment, and then we'll open up things like, we'll open up this body shell. This is actually what Alonzo would do a lot of his rigging on. It's more of a low-res wireframe, and then we use open subdiv to warp the higher-res mesh on top of this. And then they'll bring up, we have workflow-specific modes that you bring up in Presto. So for instance, you'll come in here, and then you look exactly at the numerical values on this mesh, which correspond to how the leg controls move that upper hip. So these are environments that, all these environments are inside of Presto and are using high-performance GL to be able to have these workflows come to life. Boom. Apologies for the mic problems. I hope you heard some of that.
There we go. All right. And so as Dirk mentioned, everybody is kind of working together on this shot, on a single shot collaboratively. And the way that works in Presto is that we have this notion of shot layers. They work a lot like Photoshop layers. So animation can have their layer, and crowds can have their layer, and effects can have their own layer, and everyone can work simultaneously without having to like lock a single file and wait for that person to check it back in. And so the interesting thing here is that this same structure for the shot is also used for the asset. So within Mater here, for example, he has several layers as well. So he has a geometry layer, he has a shading layer, he has other layers, and different departments can work on those things in parallel as well. The other thing that Presto, that Presto was established in Presto is this notion of references. So Mater in this diagram is being brought in twice. There's Mater 1 and Mater 2. It's the same underlying asset. He's not being like flattened into the shot. The underlying asset is live. So if you make changes to Mater, it's reflected in both Mater 1 and Mater 2, and different animations can be overlaid on top of both. And so we thought that idea was really great. We wanted to use it everywhere in our pipeline. And so we refactored that out of Presto into a shared library and introduced this new library that's called Universal Scene Description that if you understand Alembic, it's similar in spirit. It's a point cache. But it has this notion of layers and references that's being shared from the Presto animation system. So this was originally deployed on Finding Dory. We just rolled it out. We have a new pipeline, all built on USD. The scene is described in terms of layers and references, as I just described, and it's built for multi-user workflows throughout the pipeline now, not just in Presto. And it's really made for like content creation interchange. So you can use USD in Presto, you can use it in Maya and Katana, and move your assets around really freely. And so just to kind of anchor this in something concrete, here's an example. This is a valid USD file. It defines a cube that's called hello cube, and the size is 1. And we have a viewer for these things called USD view that's just kind of like our like debugger. And here's what it looks like in USD view. So not surprising. So to introduce some of these notions of layers and references, here's a reference to hello cube. And you notice this one says over, which we're going to override opinions on top of this reference that we're bringing in. And we're going to make it instanceable. And so now we have 2 instances of the cube. And so instancing is becoming more and more important as as scenes get more and more complex. Like we use proceduralism to make things complex, but also instancing is a really, really powerful tool. And so USD embodies that in a really simple way. And so we have this notion of composition arcs. So I just said layers and references, but really there's a set of different kind of operators that we call composition arcs. So layers are like Photoshop layers. Inheritance is like inheritance in a programming language. You can define a base class and then inherit from that. And so if you have 10 cubes that all inherit from a class called blue, you can change the color on it, or maybe that provides the blue underlying color. There are variants, which are like a switch statement in the scene graph. You can say I have a coffee cup with a handle, a coffee cup without a handle. It's really fundamentally the same asset. You don't want to deal with multiple assets when they're really the same. And then a variant lets you switch that handle on and off. References lets you pull in the asset into a shot or into another asset. And then payloads are kind of load-unload boundaries. So you can, at runtime, kind of load and unload things easily. And we lovingly refer to this as liver P. This is the order of kind of precedence. So layers are the strongest, inheritance are the next strongest, variants, references, and then payloads. And this order of operations is really important so things don't get crazy. And this is kind of a recursive structure, so we know exactly how to resolve all opinions that have been authored in a shot. And we have an opinion debugger that we call it that lets you go in and see exactly where all the overrides are coming from. Okay, so we have a demo of USD View now.
So we're going to show USD View. Can anybody hear me? Yeah. Excellent. So this is starting the process up from scratch. So we're going to start up the process. We're going to bring up that shot and all of the geometric complexity that was in the shot. That they were, whatever, 52 million triangles. And all of that kind of came up just so we can do it again. It's fun to do over and over again. So USD, high performance is really a fundamental aspect of USD. And here we're going to play through the shot. Again, this is not the Presto interface. This is a kind of a debugging tool that we use, designed to be lightweight at startup. But it's important to have all that geometry and be able to move around it so that you can do your filmmaking in that environment. So Hydra and USD are what contribute to that. We've got the seagrass from effects. We've got all the characters. We've got all the coral geometry.
The seagrass here is actually expressed as B-spline curves, and then we use the hardware tessellator to extrude that out.
And this is a live three-dimensional scene, so we can spin around in real time at whatever we're hitting. 62, I think we're limited by refresh at the moment, with all those 52 million polygons.
I'll switch this back there.
And USD View does come with the USD distribution.
All right. Yes. So USD is going to be open sourced at SIGGRAPH this year. There's a binary distribution available now on graphics.pixar.com. You can go check it out, download it. That build is for Linux currently, but it ultimately will be cross-platform, Windows, Linux, and Mac. So I mentioned subdivision surfaces earlier. And just so that we're all kind of on the same page, a subdivision surface starts off as this kind of control mesh that we call it. It's a low polygon representation. This is the thing that the artist actually models, and this is the thing that we pass through our pipeline. What we do is we split the faces and then average them, and we get this next representation. This is actually after a couple levels of subdivision. And we keep doing that until we get to the limit surface, and then you get this nice, smooth, kind of beautiful surface out of it. And so the low poly representation, the control cage is like 48 polygons. And then our beautiful limit surface is 1.5 million polygons. So that's that kind of like geometric growth and complexity there. If you're interested in how to model subdivs or the math that's behind them, you can go to Pixar in a Box. There's all kinds of cool stuff on there, but specifically there's some interesting stuff on subdivs as well. And so our solution for handling subdivision surfaces in the pipeline is OpenSubdiv. And so this is an open source project. It's built, it's based on RenderMan's subdivision algorithm. It's for fast evaluation, both for rigging, for preview, for actual final render as well. And it's got a broad API intentionally so that we can serve lots of different clients. So as I said, it's suitable for offline rendering and real-time rendering. And particularly in OpenSubdiv 3, we have some really, really big improvements in terms of like GPU shader configuration. Now you can render a subdiv with a single shader, whereas in the past it was much more complex. It's faster in terms of CPU refinement. In some cases, depending on the topology of the mesh, you get a 10x speed up in OpenSubdiv 3 over OpenSubdiv 2. And we really, really tried to simplify the API because that was feedback that we got from the community that subdivs are fundamentally a difficult thing to integrate in a pipeline, and we wanted to try and make that as easy as possible. And so we think both the GPU shader configuration makes it easier to integrate into render engines, and then the API hopefully makes it less kind of mind-bending in terms of like the data that you're dealing with. And we have a whole bunch of different evaluators that come with it in the namespace OSD. That's for parallel evaluation, so GLSL compute, transform feedback, CUDA, TBB. Intel recently contributed an ISPC evaluator. And then also in the FAR namespace, we have a single-threaded evaluation, which is really ideal for offline rendering. The other big thing that OpenSubdiv brings to the table is feature-adaptive subdivision. This is based on research from Mark Meyer, Tony DeRose, Matthias Niesner, and Charles Loop from, I think, 2012. And so for uniform subdivision, this subdiv turns into 1.5 million polygons, but adaptive subdivision realizes that you only really need to refine the mesh in places where there are extraordinary features, we call them. And so for adaptive subdivision, you end up with 1,000 patches. And then what we do is take those B-spline patches and send them down to the GPU, and we use the tessellator to go ahead and generate this like 1.5 million polys, and then throw it away when we're done. So we've gotten some really great contributions from a bunch of different people. In particular, I'd like to call out DreamWorks. For OpenSubdiv 3, they made a massive contribution where they helped us kind of rewrite a bunch of the internals. Barry Fowler, in particular, did a bunch of the heavy lifting there, and we just wanted to thank DreamWorks for giving him the time to do that. It was a really awesome contribution, and that 10x CPU side speed up definitely came from Barry's work. Also, there's lots of community adoption. We're happy about that. There's lots of smaller projects. I called out a bunch of the bigger ones here. So that's great. And it's available on GitHub, so it's open source as well. It's already out there. We recently released 3.05, which was just a minor kind of point release. So the next piece of technology that we want to talk about is Hydra, which is our real-time renderer, specifically for OpenGL, the stuff that you've seen so far. So it's an engine that was built for content creation. It's built on modern graphics APIs following the kind of AZDO methodology. It's using OpenGL 4.4, and it's been designed specifically for scalability and for speed. We have a whole bunch of features that we've implemented. There are a few that are worth calling out. In particular, it consumes RenderMan inputs by just natively. So the way that our data flows through the pipeline, the way that it flows through USD, we consume it exactly as it's going to go into RenderMan. We have a notion of primvars. If you understand RenderMan, maybe you know what that is. One other thing on this list worth calling out is that it's, of course, integrated with OpenSubdiv 3. It's heavily multi-threaded. And really, all this is just to say that it's been designed for film production specifically. And if you're interested in kind of more technical details and you want to understand how the internals work, you can check out our GTC 2015 talk. So instancing is becoming more and more important, as I mentioned earlier. There are two forms of instancing that we support. One is based on just saying instanceable equals true in USD, but another thing is actually having a point cloud of translate, rotates, and scales that are all bound to prototypes. So you can imagine here there's 4 instances. 2 of them are going to render prototype 1. 2 of them are going to render prototype 2. The challenge here is that the production assets have these instances kind of all shuffled around because what they want to do is render a certain percentage of the point cloud. So if you have a tree and it's way off in the distance, you want to render maybe 10% of the leaves on the tree. And you want those leaves to be representative of the whole tree. And so you shuffle the instances around. The problem is that's not super friendly for hardware instancing. So what we end up doing is we make this kind of offset table that collates by the prototype. And the reason why we do this rather than just sorting the instance table is that it makes it a lot faster. When you have animated instances, we can just stream them in. And so here, prototype 1, prototype 2 kind of go through this offset table on the GPU. And so going back to our USD example, here's rolling out instances. It's really easy to make instances. And as a result, you kind of get this new problem, which is like, yeah, okay, what about instancers that instance more instancers? And so for that, we have recursive instancing. And the way that happens is like you have the leaves on the tree, and then the tree becomes an asset, and then you instance the asset multiple times. Then, okay, now you have like recursive instancing. We kind of unroll the instance indices on the GPU and have backwards pointers that kind of chase down the parent transforms. I'm not going to go into detail there, but it's kind of an interesting thing. So Dirk is going to show us a demo of instancing.
So this is some instances that were created by Paul Konyuk, who was the crowds lead on Finding Dory. And I think this is 5,000 rays, and they're playing through in Presto. We have it limited to 24 FPS. Oh, actually, we're a little over 24 FPS. But you can grab that thing, and then you can move it around. So it's taking advantage of the high-performance Hydra stuff to be able to position a crowd of rays at 60 frames a second, and then play and see them play. So these are the kinds of ways we're trying to get around the complexity that's in production by leveraging this tech.
All right. So one other aspect of Hydra that's super important is that it's a kind of push-pull data model. So the scene graph declares the primitives that are available. It'll say, like, I have a mesh. And then it's not until you actually create a render pass and go to render that mesh that we start pulling data from it. And the reason that this is important is because these are the RenderMan inputs. We have a ton of data that's associated with every single object in the world. And so if we just aggressively pull everything into memory, you'll totally swamp the GPU, or you'll end up with a giant copy of it on the CPU side. And so what we do is only when we go to render something, we pull those values and we put them into the GPU, and we have no CPU side copy at all. And so Hydra is really kind of talking to the scene graph in a first-class way. It's like in other engines, you may, like the scene graph kind of pushes data into your renderer. But in this case, Hydra is pulling it, so we need some way for it to talk to the scene graph. So we have the scene graph adapter. And you can actually have multiple adapters and multiple underlying scene graphs. And so what's happening here is the adapter is feeding data into the Hydra render index, we call it, which is just a lightweight kind of collection of pointers off to the GPU memory that it's holding onto. And so we can have kind of a heterogeneous set of scene graphs backing it that Hydra is pulling data from. And in practice, what that means is when you're running Presto, you'll have the Presto scene graph and you'll have the USD scene graph, and they're kind of both feeding data back into Hydra. And you can have a single render pass to render both those things. You have a kind of consistent feature set to work with. What it also means is that you can integrate it with other applications. So I just mentioned Presto. It's integrated with USD view. It's the same underlying stuff. Maya, we have USD integrated in. In Katana, we actually have it integrated natively. So we're consuming some of the native Katana scene graph. The color looks a little funky here because they like to see clearly, like when you're rendering USD, they want to know that it's the cache versus the live geometry. So the live geometry doesn't have this kind of tint on it. So we've been collaborating a lot with Industrial Light and Magic recently. And so they were curious to either build something like Hydra or to maybe use Hydra for virtual production. And so that went really well. We had a bunch of talks, and then we realized that there's kind of two parts of their render engine today. They have a deferred renderer, and so they have the part that generates the G buffer and the part that actually does the shading and lighting. And so they've been using Hydra to generate their G buffer, and they use their same shading and lighting renderer to do the rest of it. And so here's the Millennium Falcon. It's about 14,000 meshes, 140 textures at 8K. Those are actually going to the GPU, which is crazy. Yeah, it worked out really well. And so it's consuming the native ILM scene graph through the same kind of adapter interface. And so Hydra is going to be open sourced with USD at SIGGRAPH. It's part of the package. It's the thing that does the rendering in USD view. Cool. I'm going to hand it off to Paul.
Hello. Yes. Yes, so now we're going to switch gears a little bit, and we're going to talk about effects. Effects, so sometimes you want to get a sense of what the scene will look like before you actually submit your shot into the render farm. It could be for multiple reasons. You might just want to save those cycles in the render farm. You might just want to get a preview. You might just don't want to spend the time maybe waiting for that. So we have built effects, and these are some of the requirements that we try to restrict ourselves. Like it has to be easy to set up and maintain. You cannot do some crazy thing that you only understand, but it has to be intuitive. It has to be a reliable approximation, and that's actually quite important because you cannot mislead the artist too much, because that will actually miss the whole point of trying to speed up his pipeline or her pipeline. And the common case, it still has to be fast, which is interesting. And also at the same time, you don't want to mess up too much with the asset build requirements. So with those restrictions or requirements, we have built something that we call the render graph that allows us to create new effects. And as you can see, it kind of defines the flow of the data in the application. So it starts on the render control, which basically provides some inputs of data and some starting point in the graph. And then, for example, in this case, it basically goes in and sets up some shadows, and then it will go ahead and like render on those shadow maps and disable the rendering of the shadows. and then it goes on into post-processing, and then you can see the siblings that post-processing runs, which SSAO and different nodes. And finally, it outputs to our cache, because we also have an image cache that you can use, so we don't have to recompute if it's the same frame, or just to a screen. And so this is really useful for multiple reasons. One, because it makes your pipeline transparent, at least for engineers, I guess. But it's really easy to debug what's going on in the scene if you have something like that, and you can see how your data flows through your pipeline before it goes onto screen. And those arrows, in some cases, actually transport data from different nodes, so they can actually communicate and build up. So these are some of the effects that are built in to Presto currently. We have some soft shadows we also have AO, reflections, refractions, motion blur. Things like depth of field, for example, can help on getting a sense of the scene, or what you're trying to do with your camera before you actually have to send that render onto the render farm, which is really useful. And I think we'll hand it to Dirk.
I'm going to show some of those effects here. Some of them, like the fur for Monsters University, we've shown before at GTC. But on Killer, as you look at this shot, you can see that there are caustics on the ground from the water to help people understand that they're underwater in this. There are shadows, there's depth of field, there's a bunch of other things going on. So let me try and pull those back one at a time. So let me go to the beginning. So here, I'll start by pulling back depth of field. So now you can see that things in the background are sharp. Depth of field is really important for layout, so we do kind of back-to-back tests with rendering to be able to give them a good sense of depth of field. And then you can see some other things going on here, like I'll pull back ambient occlusion, and you see a little less contrast around the coral on the side. The coral is done by Colin Thompson's team and sets, which is amazing. And then you pull back shadows. Now you get a lot less depth on the scene. You can pull back those caustics. There's some murk, which indicates kind of depth fall off in the water, and then some kind of shaping controls that lighting uses. So now you see the same stuff that you saw before, but a lot of the contextual context for water and depth and murk are gone, which make it harder for people to judge, for instance, the end of that shot. And then if we pull back, also we can turn off hardware shading. So as we said before, it was really important to be able to see the freckles on Dory's face and to see them move as you animate. When you pull that off, this is what we used to see all the time. You lose textural clues on the surface to show how it's moving. So we'd rather turn on hardware shading, turn on shadows, see some caustics, lighting shapers, turn on the murk, turn on ambient occlusion, turn on depth of field, and give people a more immersive sense of what that shot's going to look like in the render. It doesn't have to be totally perfect. It's just enough to give them the hints that they need to be able to do their job without submitting an expensive render. Boom.
So in that sense, the team this year has been building other effects on top of the ones that we already have. These are some of them. We got requests from production to actually be able to see some of those textures reacting in a similar way to what they do in RenderMan. And so we have now a real-time approximation to physically based shading. And this talk is not really about physically based shading, so I'm not going to go too much into what we have actually used and implement and stuff. But we're using typical games equations to solve the BRDF, and from GGX or Schleich. And if you want more information, definitely go and check some of the publications in the real-time. The physically based shading course that happens every year at SIGGRAPH from 2012 to 2015. There's been some awesome contributions, including the ones that Pixar published in 2013. And so this is a closer look up into what it looks like in real time. We also have some way to capture indirect lighting from specular and also from diffuse. And but of course, like if you think about it, we have really complex networks to define those materials. So it's not as easy as just having those textures. We need to bake those textures from those complex networks. And so for that, we use RenderMan. And you can see here some of our, like this is the textures that Buddy was using in the previous shot, like just diffuse, specular, as well as roughness and some of the displacement mapping. The problem, though, is because we want detail, we use really big textures, and that can get out of hand really quickly. If you have more than 1, 2, 3, 10, 20 characters or sets, then suddenly you run out of space on your GPUs. And you have multiple options when that happens, right? You can either buy new GPUs, or you can start trying to optimize the problem in different ways, right? We went for just the way of compressing those many textures, and we have decided to go for VPTC compression for the real-time part of it. And for the compressor, actually, we are using a similar way that we have an ISPC contribution for OpenSubDiff. We also use ISPC for the step where we are compressing the VPTC texture offline, and that happens once, and then we can just use that data that's compressed and just let the GPU decompress it. And this is some of the data that will be useful to kind of get a sense of how good the compression is. With VPTC, for non-floating points, it goes from like for 3 channels, it goes from like 48 bytes to like 16 bytes, which is kind of incredible. And then for VC6, even though it's just half floating point, it's also really, really good compression rate. And this is just some of the results that we get. They're pretty, like, you cannot really notice, which is really great. And also, we just want to mention as well the fact that all this work has to work with UVs, but also with PTEX, because depending on the department, it will use either one or the other one. Depends if they have time or if they wanted to actually go with UVs, or they just prefer to paint on it and use PTEX, like in sets, for example, or some of the backlog models that we have at Pixar from previous movies. And I think Dirk.
Yeah. So I'll talk a little bit about the pipeline that we use to create these things. We do our modeling in Maya, and we do our shading and lighting in Katana. So we want to be able to set up an environment where we can't force the artists to have to do a bunch of additional steps in order to make the real-time stuff work, because their job is to put something on screen. So we need to set up kind of more semi-automated pipelines for them to go through with minimal amount of work. So we go through and click next to the. Yeah. So for instance, in Maya, they'll have a bunch of characters used as UVs at Pixar, and they'll have a bunch of different UV sets and a bunch of tiled UV sets. So one of the things we do is we set up a single UV set that spans the entire character in one normalized space. In Maya, that's pretty quick. You can run a script and kind of set this up. And again, we do this because we don't need to be able to edit those materials when animators are working. We just need to be able to show them approximation. So flattening all of those materials and all of those textures and all of that shading into a single texture or a set of textures makes the performance a lot better. And then, so that's the resulting color pass for Buzz that's baked into a texture. And then we use Katana. We used Katana to do that. We have some automated Python scripts. You run a Python script, it drops a live group into Katana, and then samples those textures and dumps them out for the artist. So as long as they have the UV set and things, there's nothing too crazy going on in their shaders. You may have to turn on some directional specific shading, for instance, to bake it out. It comes out in a pretty automated way. And there's built-in support for this in RenderMan 21. They have some new options in the header to be able to render directly to textures, so that simplifies our pipeline with RenderMan 21. And can you switch me to 7?
Yes.
Or 5? So here's a couple of examples. This is an example from The Good Dinosaur. A lot of times we don't have things that are super shiny in our movies. So anytime we have something shiny, we like to play with it. So here's the beetle. If you remember, this is Spot bites its head off. I don't have that animated here. But you can see that we have specular color, specular reflection, we have bump, we have displacement, and specular roughness across the surface. We can get some of that color, some of that iridescent color on the back of that wing. And again, these are all live animation controls, so you can have this while you're opposing the character. It's not some offline thing that happens after you animate. It's all right in front of you. And one more. So I'm sure you recognize these guys. So this is kind of now the new level for us, the new kind of baseline for an animation stand-in. It's something that the animator uses on a daily basis. And this is Woody and Buzz. We have color, specular roughness, specular color, and displacement channels on these guys baked out of Katana. And you can see a lot of good detail here, kind of as you move in. You can see the sheriff's badge that we saw before. And again, all real time on this laptop. Displacement, bump. We've got the things across, like that belt buckle looks kind of nice. And you can see that some spots on that are shiny and some spots are not. Some spots on the belt are shiny, some are not. That's the specular roughness channels. You've got Andy's signature there, always important. And again, this is an interactive environment, so you can still mung him at 50 frames a second in this shot. A lot of these rigs were built by Seth Freeman, who's definitely an optimization guy, so I appreciate having somebody like Seth building some really high-performance rigs for us. And you can see the shadows moving across, ambient occlusion helping you see contact. And we can grab Woody's mouth controls, move them up and down. I just noticed that his teeth are black. Sorry, that's a demo problem. I will fix that for something. And then you can animate those controls at whatever we're hitting, 24 FPS, and Buzz is here. Jeremy mentioned GPU subdivision, and that's super important. Oh, quality animation there. So as you go in, and they really shouldn't let us animate. It's a good thing that they don't. So as you look at the underlying wireframe of his surface, this is what the rigger generated. That's actually what was modeled in Maya, and those are the points that they tweak when they're doing their rigging. And then we take that and we bump it up to another level of subdivision or another level of subdivision to really accurately represent what that surface is. And it can be pretty important to do that. You can see artifacts on the eyes when you don't really match the limit surface. You see some tweaks there, or the tips of fingers. A lot of things are really important to see accurate. That happens in a GLSL prepass, I think, at the moment. And again, it doesn't slow down. So we're seeing Woody has GPU subdivision being applied as he's animating. And the goal here is for animators just not to notice. And I think we've been pretty successful at that. We have all the different parts of Buzz, but we don't have to worry that these are all different G-prims because we flattened the whole thing into a single material. We don't have a bunch of complicated plumbing in the real-time environment for all those different materials and different parts. And Woody as well animates. Cool. So that's what we have for physically baked shading in Presto with bad animation.
All right, that's pretty much the end of our talk. For future work, we're looking into more kind of ground truth effects that closer match RenderMan using kind of accumulation buffer techniques. So getting depth of field that works with transparency is super important, and like accumulation buffer can help with that. Volumetric effects, we had lots of awesome volumes on The Good Dinosaur, and people want to see those in real time, so we want to get that stuff going. Real-time path tracing, there's a talk right after this by Danny Namias. He's talking about, the talk is designing surface materials with GPU ray tracing. That should be super interesting, so check that out. Subsurface scattering, this is not a ray trace subsurface scattering, but like an interactive real-time subsurface scattering so that people can see when there are like real hard creases in skin and stuff like that, they tend to like blur out in the final render, and that becomes important to see. And then, of course, we want to add Vulkan DX12 metal support in Hydra and OpenSubdiv going forward. Yes, we are hiring both GPU and rendering engineers, entry-level and senior engineers. So if you're interested, please contact us. And that's all we got.